Okay, so let's think about nucleation in a regular solution. So in this case, so let's just draw a picture of what we're envisioning. So we have a case where if we look at the Gibbs free energy as a function of composition, um, we have this double minimum, right? And we're trying to think of what happens when we start out with let's say we started out with a composition, a particular composition, above the temperature where we would have this two-phase separation, and we were at some composition here. Let's call this X star. And now we believe that it would lower the free energy, right, if we were to be able to phase separate into XA and XB, so two phases that are joined by the common tangent construction so that they have the same chemical potential, right? And we want to know let's see, how can we start the phase separation process? So we go from X star to XA plus XB, right? Okay. And we know that because we have a conserved order parameter, we know that XA plus XB has to equal 1, right? And so if we have a local increase in XA, right, that has to equal a decrease in XB. Here I'm going to call this X1 and X2 so as not to be confusing, right? Because XA is the mole fraction of species A, XB is the mole fraction of species B, and then X1 would be the mole fraction of B in phase 1, and X2 would be the mole fraction of B in X2. Okay, hopefully that clarifies that. So what's happening when we start to form this phase separation? So let's take a close-up view of G versus XB. And here we're going to focus in right on the area around X star, right? So right around here. We're going to blow that up to make this graph, right? So if we look at that, we're at some local point in G. There's some curvature. We're going to assume the curvature is positive. We happen to be at X star here. And now we want to phase separate, right? So we're going to have phase separation into X star plus delta X, right? And X star minus delta X. Okay. So now, but what we're going to notice is that when we do that, the free energy of the system per mole, right, is going to equal some mixture of these two phases, and we know we can get the free energy of the whole system by drawing a line between them, right? Because if we're an average between these two, right, the total free energy per mole has to fall somewhere along this line, And so we can kind of see just graphically that our net free energy, in order to keep the composition at X star, is going to be above where the free energy was to begin with. Or in other words, in mathematical terms, we can say that the free energy per mole is given by the free energy per mole at X star plus dg dx, right, at X star. So here I'm just doing a Taylor expansion, X minus X star, right, plus 1/2 d squared g dx. And here by x I mean xb at x squared at X star times x minus X star squared. So this is just a Taylor expansion, right? They're higher order terms, but we're not going to worry about them. And then if we think about, well, what's the change in free energy due to the fluctuation? Well, we have a delta G that comes from a certain number of moles that we've transformed into these new phases, right? And we have the contribution from the ones that we've increased the composition. We've increased X, right, plus 1/2 times the free energy per mole, and here for some portion of the material where we've decreased the value of X, right? We've created a enriched region and a region that's not enriched or that has less B, and then we have to subtract off the free energy per mole that we originally had, right? Because we're getting the difference in the free energy. So the net fluctuation in the free energy is delta N, and now we're going to use our expansion. So this will give us 1/2 GM X star, right, plus, and I'm going to write this as 1/2 G prime at X star, right, delta X, because that's X minus X star, plus 1/4 G double prime at X star times delta X squared, right? And then from this term, we're going to get plus 1/2 GM X star minus 1/2 G prime X star delta X, right? Because we'll get a minus delta X here, plus 1/4 G double prime X star delta X squared, and then minus GM of X star. So clearly, this term will cancel these two terms. These two terms cancel each other, and what we're left with at the end of the day for the fluctuation in G is that the fluctuation in G goes as delta N over 2 G prime prime, the second derivative of the free energy at X star delta X squared, right? So we can see that if the curvature of the free energy at X star is positive, right, then fluctuations are disfavored. And this is without putting in any surface energy, right? Even without any surface energy contribution, the fact that you have to phase separate locally and that's going to raise your free energy leads to a disfavoring of the fluctuation and therefore a barrier to nucleation. So even without thinking about the surface energy effect, we're going to have a region where we have disfavored nucleation. And one consequence of this is if we think about our phase diagram, right, at any point, so the phase diagram So that would be T versus XB. Okay. So in the phase diagram, we would have we know we would have composition. So above some critical temperature, we would have a homogeneous phase. Below critical temperature, we'd have phase separation into two typical compositions. But what we note is that if we're looking at one particular temperature below the critical temperature, right? So let's say this particular temperature, T0, right? That it's actually not until you get within the inflection point here that you can get spontaneous phase separation, right? So there's an inflection point here, and those correspond to points here within the two-phase region. And so these lines have special meaning. So this line out here is called the binodal. That is, inside there we get binary phase separation. That is, binary phase separation is favored but must nucleate. That is, you have to get a big enough fluctuation that you can create the second phase. And then there's the second line, which is called the spinodal. And in that region, the curvature has changed from being positive to being negative. So the change of a fluctuation is negative. That is, any fluctuation can lower the free energy. And so their phase separation is spontaneous. Okay. And so this is known as the spinodal region. If you go past the spinodal, you're in the spinodal region, you'll get spontaneous phase separation. If you're within the binodal but not yet within the spinodal, you have to wait some time to get a big enough fluctuation so that you can create the phase separation. And this is all without considering the effective surface energy so far.